Let's talk about free fall. What do we mean by free fall? Well, we mean an object is in free fall when it is only influenced by gravity. There's no rockets attached, there's nothing else pushing on it. The only thing affecting the object is gravity. By now you should have watched this video where you saw an Apollo 15 astronaut testing a hypothesis by Galileo Galilei. And Galileo's hypothesis was that in a gravitational field, all things fall at the same rate. Or in other words, all things experience the same acceleration. Now, this experiment had to be done on the moon to reduce the influence of the atmosphere and negate any air resistance. We can do this on the Earth if we put it in a vacuum chamber, and you might look on YouTube and you can find a video of that as well. Of course, when we talk about free fall is when an object is moving only under the influence of gravity, like that hammer and feather we're doing. And the rate of gravity, or the rate of acceleration due to gravity near the surface of the Earth, is a constant 9.8 meters per second squared, or 32 feet per second squared. Of course, what this means is that it doesn't matter if we have an object being thrown upwards or something being dropped from a height. Both of these objects will experience a constant acceleration of 9.8 meters per second squared. And that constant acceleration will mean that their motion diagrams will end up being symmetric. We said that the motion diagram of an object being thrown up into the air and an object being dropped from a height are symmetric under constant gravity. So when you're in free fall. And we can ask the question, well, what would the shape of this motion look like on a graph? So if we were to plot position of our object on a graph as it goes up, we would get a shape that looks something like that, where the motion is slowly going up until it reaches its highest point right there. Oops, sorry, right there. After it reaches its highest point, it'll begin to drop down. And so now we can start talking about this portion. What would it look like there? Well, it'll come back down. And it'll have a motion on the other side that is symmetric, as we said. And so we get this motion on the other side that is symmetric. So if we were to draw this in one go, we would end up with a shape that goes up, turns an arch, and comes back down. And you should recognize this as a parabola, so that we would expect our equation of motion for free fall, at least as far as position goes, to be a parabolic equation. And sure enough, if you've looked in the text, you should have read that they gave the motion, or the kinematic equation for free fall to be my final position is just my initial position plus my initial velocity times my time. And now they said minus g. I'm going to write it as plus 1/2 my acceleration, and this is a y acceleration just like this is a y velocity, times my time squared. Now, I've written this as ay, so you remember that it is an acceleration, and whether it's plus g or minus g just depends on your coordinate system. If I set up as positive, then my acceleration, if I set up as positive, then my acceleration is equal to minus g. If I set down as my positive direction, then my acceleration is, of course, just g, or plus g. And what I put in for my acceleration will depend on how I drew my coordinate system. If I choose what might be termed a normal coordinate system where up is plus g, then I will get the equation that you got in your book. We said that the shape of the position versus time graph of an object in free fall is parabolic. And why does this matter? Well, this tells us that for any object in free fall, we already know certain values. At any given point on this curve, we know that the velocity is just the slope of the tangent to the line. Well, there is a point on this curve where we absolutely know the value without ever knowing the function, and that is right here at the top. At the top of this curve, we know that the slope will always be flat, so that at this point, my slope is just 0, which means that my velocity at this point is always 0. And because of this, then, we know quite a few things about free fall motion that we can add to our toolbox whenever we encounter it when we're trying to solve kinematic equations. Now, I will say you do have to be careful and make sure you're at the top of the slope. If, for example, I throw an object up into the air so that it has some initial velocity, well, that is going to follow a parabolic trajectory. And sure enough, right here at the top, its slope is going to be 0. However, if I instead take an object and I throw it towards the ground from a height, well, it's sort of like we're starting on this part of the curve, and we end up getting a curve that is just part of this parabolic shape. Because we've already started with some zero or some non-zero velocity, and we're starting at our highest point, so the shape of our curve will be the backside of this parabola, but we won't start off with a velocity of 0. We start off with some velocity that is not 0. So you do have to be careful about how you're setting up problems. But if we're dealing with things flying up into the air and then coming down, or if we're dealing with things that we just drop, then they will either start off at this point or have reached this point when it reaches its highest peak. When we put these ideas together, we arrive at what might look like special equations or special forms of the kinematic equations, but really all we've done, you can see, these equations are the same. All we've done is assign acceleration to b minus g. Once again, I want to emphasize that this is only because we set up as the positive direction. We've done the same for these equations, and we've done the same for these equations. So if you understand how to use the kinematic equations in the first place, free fall is just easy. All we've done is we've now said we don't have to look for the acceleration anymore. We already know it. It is gravity. And that is then 9.8 meters per second squared.